Hi there, welcome back to our course Advanced Quantum Mechanics. This is the last and 36th lecture in our course. Remember that at the beginning of our course, we discussed levels of abstraction, how numbers are the lowest level of abstraction, and then above that there are variables and functions and then differential equations, and then the Hamiltonian principle or the Lagrangian principle, the action principle. So we had this hierarchy of abstraction where we said that on top are the Hamiltonian or the Lagrangian formulation, and then from that, solving various problems, eventually we arrive down at number predictions for observables. The key step that we performed was to arise from the Newton formulation of classical mechanics in terms of differential equations up to the more abstract level of Hamiltonians and Lagrangians, and then we were able to do this quantum mechanically, either with the operator formalism, canonical quantization, or alternatively with a path integral. Now today, I'd like to show you a glimpse of what's further up. So let's ask, is there a higher level here? Is there a higher level principle, a higher level of abstraction at which we can derive Hamiltonians, from which we can then derive equations of motion and, time evolution operators, Green's functions, predictions, etc. What could that higher level be? And it turns out there is a higher level. It's fairly established. Modern physics doesn't really go much higher than the level that I will explain now. It's the gauge principle. And much of what the frontier of research is today can be framed as trying to understand the next higher level there above the gauge principle. So today we'll do the gauge principle. I have to say the gauge principle is not doing a complete job, at least not yet. We can't really derive Hamiltonians or Lagrangians completely from scratch. The gauge principle does predict, however, how, given a certain Hamiltonian, we can predict what additional terms should be added to the Hamiltonian, and therefore what additional physics there should be around. So you know a little bit of physics, and the gauge principle gives you a means to guess what more there should be. And that gauge principle has been very successful in predicting from simple Hamiltonians how to get more extended ones that describe more of the physics that's going on in nature. Let us start with the simplest example. Simplest example of the gauge principle. We start with a free electron. Let's say we have h hat equal to p hat squared over 2m. And this is meant to be the 3 momentum squared. So we have an electron. It could also be a proton. It's just some charged particle. And it's evolving according to this Hamiltonian. Then the gauge principle starts with the following observation. Namely, as we observed earlier in this course already, when we do what is called a global gauge, namely, we take the wave function of our system, such as our electron, and we globally gauge it by mapping it into a gauged wave function, psi tilde of x, which is defined to be e to the power I alpha psi of x, then that's what we call a global gauge transformation. And it turns out that under global gauge transformations, all predictions of our theory stay the same. All predictions are invariant. How do we see that? Well, if we calculate a prediction such as f bar, then how do we do that? Well, it's psi of x star, and then f hat. The observable is some polynomial in the x hat and the p hat operators. And since we have them act on position wave functions, we should be consistent here with the notation and put a dot there. Remember, that's the shorthand notation for this is the action of the momentum operator on position wave functions. This is the action of position operator on position wave functions. And the p hat dot, if you remember, it works like this. P hat dot acting on psi of x. We derived that this is minus h bar d by dx. Let's say p hat I psi of x. So again, here the x is a 3 vector and there are 3 position operators, 3 momentum operators. We just don't want to carry around the indices all the time. So this is before the gauging. Before gauging, this is the way that we calculate a prediction. And now after gauging, well, after gauging, what do we have? Then we calculate the integral over psi tilde of x star f hat x hat dot p hat dot psi tilde of x d3x. And of course, you know how this plays out. This is the integral of psi of x e to the power minus I alpha. There's a star. And then the f hat of x hat p hat and e I alpha psi of x d3x. And clearly this factor cancels that factor and we are back to f bar. And so therefore, indeed, all predictions remain the same under what is called a global gauge transformations. And it is called global because it's the same value of alpha everywhere. Alpha does not depend on x. Now, let us consider local gauging. Now consider a local gauge transformation. Well, in this case, things go wrong, at least initially. Namely, what we now have is that psi of x under the gauge transformation goes into psi tilde of x, which is ei alpha of x, and then psi of x. Well, now predictions are being affected by this. Namely, let us calculate before. Again, so that's f bar equal to the integral psi of x star, and then f hat x hat dot p hat dot psi of x d3x. And afterwards we have the integral of psi of x star e minus I alpha of x, right? That's the psi tilde of x now, star. And then we have f hat x hat dot p hat dot and ei alpha of x, psi of x, d3x. And these two expressions, the before and after, are not the same in general. And that's because even though this is a number, I mean, this is number valued, but it's a number valued function. That's a number valued function. And this thing here has derivatives with respect to x. So whenever our observable contains momenta, then these momentum operators are going to act on everything that's to the right, and that's both of those functions. This thing gets differentiated, so we end up having an additional term here. Let's work out how that additional term looks like in a particular example. So let's say we choose that our observable is simply one of the momenta, p hat I. Then what we have, p hat I is equal to minus IH bar d by dxi. Okay, now let's again look at the before and after. So we now have before, we have pi bar, which is the integral psi of x star, and then minus IH bar d by dx I psi of x d3x. All right. But afterwards, after gauging, what do we get? We get that we have the integral psi of x star e to the power minus I alpha of x, and then minus IH bar d by dxi, so far so good, ei alpha of x, psi of x d3x, which is equal to the integral psi of x star e minus I alpha of x. And then it's, by the product rule, the sum of two terms on the right. One term is the one that we want, where the derivative acts on psi. So we have here ei alpha of x, those two guys cancel, and we have minus I d by dxi acting on psi of x, d3x, but we're not done yet. See, this plus integral psi of x star and then e minus I alpha of x, and then we get the term that arises from differentiating our gauge function. So we get minus I, sorry, IH bar d by dxi acting on ei alpha of x, and then the result of that is multiplied with the psi of x d3x. And you see, this is an extra term. That term here matches exactly what we had up here, but that is, this extra term is messing things up, and therefore not the same, which means we don't get away with this. We can't just willy-nilly change our the phases in front of wave functions and then expect that the predictions stay the same. They don't. We have an extra term here when we do a local gauging. However, and this is where the gauge principle kicks in, the gauge principle says there is a way to fix this. There is a way to change gauge transformations and to change how the momentum operators are defined such that we can allow ourselves arbitrary gauge transformations, local gauge transformations, and no prediction changes. So the gauge principle now says the following. Gauge principle makes local gauging possible. Now, how? Well, we look at what kind of term we get here from the local gauging. Namely, it's a derivative of this gauge function here. And what is that going to give us? This is going to give us a term which is minus h bar and then d by dxi of alpha times the phase function, right? That's the extra term. That's the offending term that makes it impossible to do the local gaugings without changing the predictions for observables. So the gauge principle consists of the clever observation that there is something we can do to change the rules of the game a little bit, such that under these modified rules of the game, of what it means to do gauge transformation, we can keep all predictions invariant and therefore endow our theory with a so-called gauge symmetry. Now, how does it do it? How does the gauge principle fix things? Well, first of all, we introduce a new field. And one might think this is a high price to pay. We have to introduce suddenly something completely new that wasn't there before. True, if this new thing that we introduce is just some mathematical artifact, we would consider it a high price to pay. But it turns out that this new field that we are now introducing, let's call it A of x, will have physical significance. Therefore, the gauge principle will have led us to the introduction of this new field. It helps us predict new physics in this way. And it will help us predict what the Hamiltonian for this new physics will be. Okay, but I'm a little bit ahead of myself here. So the gauge principle makes local gauging possible by doing this. First of all, we introduce a new field. Let's call it A of x. It's going to be a vector field. And we use it to redefine what we mean by the canonical momenta. So, namely, p hat I dot psi of x, the new p hat I dot obey, by definition, obey by definition. So the new momenta acting on wave functions are going to do this. They're going to do minus IH bar d by dxi. So far so good. That's what they would have done previously. But we add here an AI of x, a vector field. And this is now multiplying the psi of x, right? So the gauge principle says we need a new field. And we add it to the action of what the momentum operators are doing. Ultimately, of course, we're adding here a term so that we can compensate for the extra term that arose from the application of the product rule earlier. So what are we going to do with this new term? Instead of just having it hang around, the second step in the gauge principle is to say that the gauging is defined to affect or transform defined now to transform both psi of x and also a of x. So the gauge principle says when you do a gauge transformation, so when you do psi of x goes into psi tilde of x, which is e to the power I alpha of x, psi of x, then you also have to transform your new vector field A of x into a new vector field A tilde of x, which is defined to be, both of them are definitions, defined to be the old vector field minus h bar and then the gradient of our gauge function alpha of x. Remember what the gradient is? Gradient of alpha is equal to d alpha by dx1, d alpha by dx2, d alpha by dx3. That's how a gradient is defined. Which I hope you remember from electromagnetism, where it comes up all the time. Now, this means, therefore, we have that also the new canonical momentum, p hat I, maps under a gauge transformation into p hat tilde I. And how does it act? Well, it is going to be the old p hat I minus h bar Laplacian, not Laplacian, nabla of alpha of x. Right? And why is that? It's because the momentum operator contains a, right? And a changes by subtracting h bar gradient of alpha. Remember, the momentum operator acts like this. The new momentum operator acts like this. And since under a gauge transformation, psi changes, but also alpha changes, and alpha changes by subtracting h bar nabla alpha, we have that also the action of the momentum will change, namely in this way. All right, so we have that psi changes under a gauge, a changes under a gauge, and therefore it's implied that also the momentum changes under a gauge. Then the proposition is that under these local gauge transformations, all predictions for observables are invariant. Which is to say, now we have arrived at a theory that has a much larger symmetry, because we can now leave the theory the same, because all of the predictions are the same, even when we choose arbitrary local gauges. So again, what is exactly the proposition here? The proposition is that f bar, the prediction for an observable, which is before calculated in this way. It's the integral of psi of x star and then f hat of x hat dot p hat dot. Remember that these p are now the new canonical momenta, the ones that have the A field in them, and then psi of x d3x. Okay, so this is before, and then after, the claim is that this f bar is f tilde bar, which is the integral where everything has been gauged, has a gauge transformation been applied. So we have psi of x tilde star, and then we have f hat of x hat dot, and then the p hat, well, there's a tilde now on those. You could also put a tilde on the x's, but the x's simply don't change under a gauge transformation, but the p do change under a gauge transformation. And then here we have the psi tilde of x, d3x. The claim is that all observables have the same predictions now. In order to prove this, we should do it for all observables, but it actually suffices if we do it for one of the momentum operators, because then if it works for one, it's easy to see how it works for any polynomial or other function of the momentum operators. So we prove this. Proof. So we choose the case of the observable being equal to one of the new canonical momentum operators. Then what do we have before the gauging? Before the gauging, we have that the expectation value for the momentum is equal to integral psi of x star, and then the operator is minus IH bar d by dxi, and we are not done yet, because remember, we introduced a new field, plus AI of x, and then psi of x d3x. And this gives us, just for later comparison, this gives us two terms, right? It gives us the term of psi of x star and then minus IH bar d by dxi. Actually, I can just remove, cannot, because there's a minus sign and then it's a psi of x and then plus psi of x star AI of x psi of x d3x. I just wanted to spell them out because later we will have to identify the one and the other when they arise in the after picture. Okay, so after the gauging, what do we have? Well, then we calculate pi tilde bar. So this is the gauge transformed momentum. Remember, the psi gets transformed, the A gets transformed, the P gets transformed. So what is this then? This is the integral of the transformed x star, and then we have the P tilde hat I, and we have psi tilde of x d3x. All right, let's spell out what this all is. This is then the integral of psi tilde of x star, and then here we have minus IH bar d by dxi plus a tilde I of x. This thing has been transformed, and then here we have the psi tilde of x d3x, and this then is the integral. Well, we know how this transformed. This is coming from psi of x times e to the power minus I alpha of x. And then here we have minus IH bar d by dxi plus, well, remember how this came about. This was the AI of x. And then let's look up exactly how it went. The gauge transformation of the A field was that the A went into a tilde, and the A tilde is a minus H bar gradient of alpha. So minus H bar gradient of alpha. So it's minus h bar d by dxi of alpha of x. And then here we have ei alpha of x and psi of x and d3x, right? So this is the transform psi, this is psi tilde, this is psi tilde star, and this is the transformed canonical momentum operator. Plenty of terms here. Now, let's see. This derivative here is going to act on this product of two functions there. And what are these two terms giving us? Well, this is going to be minus IH bar. Let's put it here. It's E I alpha of x times minus IH bar d by dxi psi of x. That's one of the two terms that we get, right? This is the term that arises when the derivative acts on the psi rather than on the phase function. But it can also act on that phase function. And what does it do? Well, we have a minus IH bar times this. Well, here we get down a factor of I times the derivative of alpha. So we have minus IH bar, and then we have I times d alpha by dxi. And we have e to the power I alpha of x and psi of x. Right, so now we have the following terms. We have this multiplying, in this bracket, we have this term, that term, and those two terms. So let's see, there's some cancellation going on, namely, we have that this term is minus h bar, derivative of alpha. And here we have plus h bar, derivative of alpha. Those two terms cancel each other out. Now that's nice. Let's see what we have left over now. So what we have left over is the integral psi of x and then e minus I alpha of x. And then we have this term left over. So that's a term e I alpha of x and minus IH bar d by dxi psi of x. And we have this term here, so plus AI of x. And all of that is multiplying EI alpha. No, sorry, that term is already in. It goes here, EI alpha of x, and then here psi of x, d3x. Okay, so now we have that this cancels that, and we now recognize that what we are left with is exactly matching the two terms that we have in here. These are exactly the two terms, and therefore we can conclude that this is equal to pi bar. So the before and the after prediction for the momentum is the same. Now, if this is true here for one power of the momentum, it's true for any power of the momentum, because what was going on here is simply that this derivative is producing an extra factor from the phase in psi tilde, which is then immediately eaten up by the extra term that arose the A tilde, right? The A tilde under gauge transformation spawns another term, namely this one. On the other hand, the psi under gauge transformation gets an extra factor, which is being picked up and differentiated with respect by this one. And those were exactly those two terms, and they cancel each other. So even if we had now the 100th power of this momentum operator here, it would still be the case that each power produces both a derivative term, but also the A produces a term that cancels it. And so what we conclude from this is that indeed we have that the F bar is equal to the F tilde bar. All observables come out the same before or after a local gauge transformation. So the gauge principle allows us to perform a much, much larger set of operations on our wave functions. Namely, we can multiply them now with arbitrary phase factors that depend on space, and we still get that all the predictions come out the same. The price we had to pay, if you want to call it a price, is that we had to introduce a new field A of x, and the A of x field had to transform in a particular way, and this was affecting the momentum operators. But once we do this, yes, we have a theory, a new theory, which has the feature that it has an extra field and it has a much bigger symmetry. Namely, the symmetry of leaving everything invariant under local gauge transformations. So it seems we gain a lot, namely we gain a larger symmetry, we gain a new field, A of x. We kind of predict here that the new physical field should exist, A of x. And that sounds all great, because it appears that we have now generated a bigger Hamiltonian. Namely, remember that we had that h hat was equal to p hat squared over 2m, but now we have that h hat, after we implement the gauge principle, we have that this is actually 1 over 2m, and then the p hat is, if you remember, it's acting, let's put a dot in here, it's acting as minus IH bar nabla. This is how the momentum operator acts, right? So we have that p vector hat dot is equal to minus IH bar nabla, plus plus the A vector field, right? Plus A of x squared. And so we see that we have an extended Hamiltonian here. We now have a Hamiltonian that contains the old term, the old p squared over 2m, but also terms that involve the A. So we have operated on a higher level of abstraction because we have now generated a new Hamiltonian. All of that sounds great, but what is this A field? And there seems to be right away a big problem with the A field. And that's because if we ask, can A of x be a observable field? Then the answer has to be no. And that's because A of x depends on the gauge we choose. You see, if you have A of x and then you choose a different gauge, then it goes into A tilde of x. So you gauge it to become the old A of x minus h bar gradient of alpha of x. Now, if A of x was a vector field that is actually measurable, well then that should not happen, because what gauge transformations we perform, with what function e to the power I alpha of x we multiply our wave functions, that's a human thing to do. Nature cannot care about that. It's like coordinate system dependent things. It's like Hilbert space basis dependent things. No, A of x can't be observable. But still, it ought to describe some physics. And indeed it does. In a subtle way, namely the A field contains something which is actually independent of gauge transformations. Actually, A of x contains a gauge invariant part. Now, in order to see this, I need to remind you of some math. Recall some math. Things that you've probably seen before, for example, in electrodynamics. So here's the definition. A vector field V is called a gradient field if there exists a scalar field lambda, so that V of x is equal to the gradient of lambda of x. Right? So if V of x is d lambda, remember this is d lambda by dx1, etc. Right? D lambda by dx2, d lambda by dx3. All right, next definition. For a vector field W, its curl is defined this way. The curl, let's call it the vector field C of x, is nabla cross product with W. And what is this? Well, the components of that are dw by dx3, dw2 by dx3 minus the other way around, dw3 by dx2. And then you move up the index by 1. So now you have dw3, dx, well, after 3, you have 1 again. 1 minus dw1 dx3, and then the last component is dw1 dx2 minus dw2 dx3. Okay, so that's the curl of a vector field. And then let me remind you of an important proposition. Proposition is that the curl of every gradient field vanishes. So what we have is that the curl of a field that's the gradient of a scalar field is equal to 0 for all scalar fields lambda. Why would that be so? Well, let's see. It's a vector field. What's the first component of that vector field? Let's call this thing here vector field M. Right? We want to show that this vector field M is 0. So then what is M1? M1 is, well, what is W2 in this case here? This is going to be d lambda by dx2, right? So this is d lambda by dx2, differentiated with respect to dx3. So we have d by dx3 minus, and then this one is d lambda by dx3, d lambda by dx3, but differentiated with respect to dx2. So d by dx2. So this is 0. And similarly, m2 equal m3 equals 0. Simply because d by dxi, d by dxj is equal to d by dxj, d by dxi. And so, yeah, the curl of a gradient vanishes. Now that's a super important observation for the gauge principle, because here, for the gauge principle, what do we have? Well, we have that if we define the following, so define, let's define a vector field B of x, which is the curl of our vector field A of x. Then this vector field B of x is immune to gauge transformations. Let's see. So it is invariant under gauge transformations. How do we see this? Well, let's see. We have that under gauge transformation, we obtain a B tilde, so this is before, and now we do the after. After gauge transformation, we have B tilde of x is equal to the curl of the A field after the gauge transformation, right? But what is that? This is the curl of the A field as it was before minus h bar, the gradient of lambda of x, because that's how the gauge transformation of the A field is defined. So therefore, this is what? This is the curl of A of x minus h bar, the curl of the gradient, right? But this, which is said, is equal to 0. This is equal to 0. So therefore, this is just the curl of A of x, which is the original B of x. So what we've uncovered here is that the curl of our vector field A is immune to gauge transformations. Therefore, that curl could be physically observable. It is something that is not dependent on the human-made choice of gauging. So, therefore, B of x may be observable. And indeed, experiments show that, yeah, B of x exists, and it's observable, and it's the magnetic field. Magnetic field. Now, that's fine. So the gauge principle led us to introduce the magnetic field. And it also tells us how the magnetic field is interacting with our electron. And that's because, as we saw earlier, we have that in the expression p hat squared over 2m, now the p hat contains the A field and therefore contains its curl, the B field. And so therefore, what used to be just the free Hamiltonian of a free electron is now the Hamiltonian of an electron that couples to the magnetic field. And there are multiple terms here because, as we saw earlier, we get all this business of the squaring, right? This here. We used to have just p squared over 2m, but as a gauge theory, we have enlarged this because our p operators become this. And so therefore, we actually get here 4 terms in the Hamiltonian now. We get the usual nabla squared over 2m, but we also get terms with derivatives and the A field and also an A squared term. All right, so then we can ask, well, all right, but what is the Hamiltonian for the A field itself? So, question, we have now a bigger Hamiltonian, bigger H hat for the electron, namely we have Hamiltonian equal to p hat squared over 2m, where this is now containing A, and so also B. But what would be the energy? But what is the energy H hat of the A field of A? It itself also ought to have some evolution, right? So what's the energy H hat A of the A field? Well, I should spell it out what I mean by it. Well, H hat A should be scalar and gauge invariant. And what could that be? Well, A itself is not gauge invariant, but B is. So, simplest ansatz, H hat A is up to some constant that has to be measured in experiment. It ought to be something like B dot B, right? Because that's going to be scalar, vector dot vector, and it's also gauge invariant. And indeed, this is true. This is how the Hamiltonian looks like for a magnetic field. So this means that the gauge principle, when applied to just an electron, has led us to predict the richness of the presence of a magnetic field. Not only that there ought to be a magnetic field, that there ought to be a field A, but also how it has to interact with the electron, because it was a very particular way that it had to be in the canonical momenta, such that the way that the A field transformed was just undoing what the derivatives did to this space-dependent phase factor. So the gauge principle not only predicted the existence of an A field, but also exactly how it interacts with the electron, and also gives us a good hint as to what the Hamiltonian might be of that new field, the magnetic field. Now, I gave you just the simplest case. The complete story is, of course, complete approach allow e to the power I alpha of x and t. Now, if you also allow the time dependence, you can again go through the gauge principles. And what you then find is obtain the electric potential and electric field. So in total, we obtain the electromagnetic field. How it couples to our charge and how its own Hamiltonian should look like. Now, at this point, you might say, oh, big deal, but we knew electromagnetism long before quantum mechanics came along. Maxwell had already all the Maxwell equations, and he knew how charges couple to the electromagnetic field. That's true, and yet the gauge principle is more than just cool in that it could retroactively post-dict that there ought to be an electromagnetic field. No, in fact, similarly, you can also extend the gauge principle to wave functions psi of x, which have an additional index here, a. And we could have that a equal to 1 or 2, or we could have that a equal to 1 or 2 and 3, and maybe even a equal to 1, 2, up, 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 capital N. And then, what is a gauge transformation? So psi now is actually a vector, right? So we have now psi of x equal to, and then we have psi 1 of x, psi 2 of x, psi 3 of x, for example, and maybe more terms. Then what corresponds to changing the phase? Well, sure, we can still just multiply our wave function with e to the power I alpha. But you see, this is a vector. We could actually gauge in this way. We could say psi tilde of x is equal to, and then here we have a matrix acting on our psi 1 of x, psi 2 of x, psi 3 of x. In the case, for example, where we have these three. Now, if we choose this, just an element to be of, for example, the unitary group U3, unitary matrix that has 3 by 3 components, then global gauge transformations are going to be fine. Local gauge transformations are not. And then we have to go through the gauge principle again, slightly modify it, because these matrices, unlike complex numbers, don't commute with other U. I mean, one U of one unitary 3 by 3 matrix doesn't generally commute with another unitary 3 by 3 matrix. Also, you could question, why should it be unitary? Maybe you can get away with an orthogonal group or a symplectic group or whichever group. And for each choice of how many components and what kind of group, you can, for each choice, you can go through the local gauge principle, develop a local gauge principle, and each time you will predict or motivate, predict new fields and their Hamiltonians. Now, what are the successes here? The successes are U2. So if you have just two components and then you have 2 by 2 unitary matrices locally, together with the U1. By the way, what is the unitary group U1? Well, that's just what we worked with in this lecture today. Namely, these are unitary 1 by 1 matrices. Now, what's a 1 by 1 matrix? It's just a number. And unitary means that the dagger of it is its inverse. Now, for a complex number that's a phase, it's true that its complex conjugate is its inverse. So these phase gauge transformations that we worked with today are called U1 numbers. So the U2 somehow mixing together with the U1 that we talked about today leads to the prediction of the W and Z boson fields along with photons. And this is what is called the electroweak theory. Electroweak theory. So this is the theory of the electromagnetic force and the weak force that is responsible for radioactivity. You see, this is pretty neat because it's very simple, just the U2, and then combined with the U1 that we have from electromagnetism, we obtain this neat theory there. But also, we can then say, what about U3, locally gauged? In this case, we obtain QCD, we obtain quantum chromodynamics, which is to say, this introduces now the gluon field. Gluon field. So what are the photons for the electromagnetic field? Now we have the gluons for the U3 symmetry, where we had the W and the Z bosons playing the role of the photons in the U2 theory. So all that is pretty cool because these are fundamental forces of nature. And then somewhat similarly, but not quite the same way, why not the same way? Well, for the U1, U2, U3, we have that this index here is not a space-time index. This is not a 3-component or 3+1 component vector that transforms under Lorentz transformations. No, no, no. This is what is called an isospin. And it's really not related to spin at all. It's an isospin, it's an internal degree of freedom. However, what might also count as a success is that gravity, that is to say general relativity, can be viewed as a gauge theory too. And what is the local gauging here? Local Lorentz or Poincaré transformations. And this is why it's only somewhat similar to what we had before, because now we are transforming under Lorentz transformations and Poincaré transformations. This is not an internal symmetry, that's an external symmetry. That's a symmetry of space-time. And notice how weird it is to do local Lorentz transformations. Ordinarily, when you Lorentz transform, you transform everything everywhere the same way. But if you allow yourself to do locally different Lorentz transformations, you can do that at the expense of having to introduce gravity. Now, you may say, okay, does that mean that if we now go on from U1 and U2, U3 to U4, U5, U722, then we get so many new forces in nature? Apparently not, we don't. It has been tried, of course. And for example, the U5 symmetry is a candidate for what is called the grand unified symmetry theory, where we make use of the fact that the U2 and the U3 and also the U1 are all subgroups of a U5. So it could be that all forces are really just one force, if namely the whole thing is reducible to just one gauge principle for one set of isospinor vectors that have, let's say, a U symmetry. Unfortunately, the predictions that you make when you start with these ansatz of a U5 seem to run into contradictions with experiment, in that you predict that the proton would not be stable. It would decay faster than one would expect. In fact, we have never seen a proton decay, but these grand unified theories predict it to decay at the time scale such that it would have to be observable by now. For example, neutrino detectors should be able to see that. So somehow, the gauge principle is on one hand super powerful in that it has led physicists historically to the correct theories for the weak interaction and the strong interaction, the U2 and the U3 symmetries. And also gravity can be viewed as a gauge theory. And yet, we still don't know why some groups, such as the U1, U2, U3, and the Lorentz transformations or Poincare transformations, are singled out. Why the gauge principle should use these, but not others. We don't know that. And that means that coming back to the very beginning of the course, where we said there is the top level for the course of the Hamiltonian, and then eventually down to predictions F bar. Higher than this is the gauge principle, but what is higher than that? We do not know. Quantum gravity candidate theory, such as string theory, tried to explain it, but so far, not really with success. We need fresh ideas to explain why the gauge principle should be employed and why in the way that it does. You see, the gauge principle singles out the position representation because we're gauging locally in position space. But if you remember back to the rest of the course, position space was no better than momentum space or any other basis in the Hilbert space. Somehow the gauge principle singles out position space. Why? The gauge principle singles out particular symmetry groups, U1, U2, U3, and then the Lorentz group. Why those? What we need is a theory that explains the gauge principle. And it is likely that the fundamental theory of quantum gravity that is yet to be developed will require us to understand the origin of the gauge principle and why it applies in the way it does. As I said, lots has been tried in that regard, but nothing has fully worked. We don't know what's above here. We don't know what this is, this question mark. And we need fresh ideas there. I leave you with this. It was fun to teach this course. I hope you enjoyed it as well. I'm hoping to teach next year in the fall term, in the fall of 2021. I'm hoping to teach my grad course Quantum Field Theory for Cosmology, which is introducing quantum field theory, which is really what is the next higher level of quantum theory. I mean, we just did quantum mechanics here, but it needs to be applied, for example, to the electromagnetic field, to the weak field, to strong field, and so on. And then in the term of winter 22, so not the coming winter term, but the winter 22, I'm planning to teach, oh wait, the other way around. In the winter of 22, I teach quantum field theory. In the fall of 21, I teach general relativity and general relativity for cosmology, including all of the mathematics of homology and cohomology theories, the sort of thing that comes up when you look at gradients and curls and why is it that the curl of a gradient is vanishing, and all of that is just the tip of the iceberg of a much bigger theory of cohomology. But these are grad courses. I also want to recommend to you to take next term, now in the winter term it's coming up, the Advanced Quantum Theory course by my colleague Eduardo Martinez, which will probably be really great. And you should be very well prepared for this now, having taken this course. Okay, so I wish you all the best for the final exam and then for the holidays. Bye-bye.